Good afternoon, everyone, and thank you for inviting me, in some sense, to come back to Peer, where I did a lot of the work in the early 2000s all the way until 2010, where we dealt with a lot of things that were individual buildings, individual bridges. But today we deal with communities, which are, in some sense, compositions of people, infrastructure, assets, values, societies that have a shared future. And we recognize that resilience is a way for us to model the process of coming back together and making things whole after a disaster. And so, as you heard today, there is a lot of issues here. There are societal issues, there are social issues, there are healthcare issues, economic issues, labor issues. We can go down to availability of workforce and resources, and then back to the quality of the infrastructure and the buildings. And in this talk, I would like to focus on infrastructure systems under the hypothesis that they are fundamental to making the recovery effort and, in some sense, putting back together the community. This graph I like because it points to the main function that civil engineers have taken onto themselves historically, and that is the provision of public safety and individual safety in individual buildings. However, the functioning of a community is much more complex, and in the very next layer is the provision of services by the infrastructure systems that give us energy, water, sustenance, communication. And then, on top of this, we build other important societal functions. I will not address the other ones, and Professor Baker has talked about this, Dr. Zurich has also talked about this, higher level functions, which are quite important. But nevertheless, what we want to do is to somehow engineer these things. To get to the engineering state, we need a model and we need the metrics. We need an acceptance criterion of when resilience is good enough and when it is not. And here we go back very often to the MCR or the Bruno model of a recovery curve or a resilience triangle, in the sense being able to quantify, or at least attempt to quantify graphically or iconographically, the way that the process of the loss of a function is represented at the time of the event, and then the process of the recovery goes on. And there have been a lot of philosophical, to some sense, discussions of how well that process goes. Is there adaptation? Is there a complete loss of a community, which could be characterized as depopulation, people leaving, or are we somewhere in between? But what I want to talk about today is a slightly different way to characterize, to quantify resilience. And this model applies to civil infrastructure systems specifically, but could possibly also be extended to economic systems or even a hospital, a healthcare system, in the sense of supply and demand comparison. And here, for an electrical power system, there is a clear distinction of facilities that provide electricity supply, the transmission lines that connect the suppliers and the consumers, and the demand posed by the consumers, be they industry, housing, or other forms of use of energy, electric power energy. And here, the reason why we focus on the supply and the demand is because we can distinctly formulate the resilience curve, the resilience triangle, this swoosh-like curve, for infrastructure supply systems. And yes, they suffer damage, yes, they recover over time, and yes, the recovery depends on the readiness of the system or this infrastructure system to do the recovery process. This is the supply side. On the demand side, we have a very similar curve. Let's just imagine for now that this relates to buildings only and people in those buildings. With damage, the buildings are depopulated, perhaps the people are transferred outside of the community enclosure, and they are in emergency shelters, but they do not pose a demand on the community that has been affected by an earthquake. And as the recovery goes, and here, for example, a little bit more slowly for housing, we have the recovery of the demand too. Put together, these two curves let us formulate what we ended up calling lack of resilience, and that is this situation when there is unmet demand for a certain service. Power, water, communication, for example, that lasts for a while after an event. And the dynamics of recovery of the supply systems and the demand systems in a community is intertwined and doesn't go as smoothly as represented in these graphs, but it's worth modeling. Also, the lack of resilience as opposed to the functionality we feel is a little bit more plastic and more accessible way of assessing this critical situation in the community when the services are lacking. And even though afterwards the overall balance may not be satisfactory, there is still a situation when people who want to use the service can do so. To do this model, we developed another system, another approach that consists of several modules, the supply capacity module, the demand modules. There is also a network service module that is built into this together with the state of transmission lines or communication lines, the roads, for example, together with a certain recovery resource amount, the recovery rates that you could do very simply, or you could also use construction management principles to establish. And all this we call the records framework, and there is a reference to that, so you can read up a little bit later. But as you may assume, there is a great similarity. This is building on the peer performance-based design and evaluation framework. There is clearly the hazard module. There is clearly the vulnerability module. There is a newly placed recovery module, which we did start to talk about towards the end of peer, and now these modules have grown up in their maturity substantially. And then finally, there is a resilience module, which in our case focuses on infrastructure systems. The one thing that I want to emphasize in this particular talk is the role of interdependency. It is quite clear, without even trying to give you any specific examples, that recovery of one infrastructure system depends on the recovery of the other, and that the overall functionality on the demand side, be it a building, be it a school, be it a hospital, a factory, a Google facility, for example, depends on the synergy of the recovery of that infrastructure piece of infrastructure physically, as well as other services that serve it, water, power, communication. And this interdependency among structural systems is key to more accurately modeling the resilience of the entire community. And what I'll illustrate this with is a relatively simple fictitious community that's somehow been made so that the elements of the community feature supply and demand or consumption units that figure in terms of the electrical power system, the cellular communication, and the water supply system. Here, the cellular communication is kind of particular because we really don't have physical infrastructure to transmit radio waves, and in that sense it is one of those virtual-ish connection systems which is very different from the transmission line, the physical, or the roadway, the physical connectivity, or the pipeline, the physical connectivity between elements of different infrastructure systems. Clearly the community also has inhabitants, industry, and also housing that generated the demand. And before an earthquake there is a certain balance, in fact more than a balance, because our infrastructure system usually runs with some supply margin reserve. However, the interdependency is what we wanted to model, and here we try to establish a model of interdependency that is not fixed. It is rather a dynamic one, because every element of the model produces certain supply and demands certain resources to function. So for example, a power generator needs cooling water and communication to work correctly within a power system. The cooling water comes from the pumps that in turn need some electricity. And so even within just the infrastructure systems, there is enough interconnectivity and complexity and closed loops to require pretty sophisticated modeling. And as opposed to a relatively standard approach of a fixed interdependence or a connectivity matrix, here we are trying to establish it dynamically, so as every resource is damaged and recovers, there is a dynamic balance of the resources it requires to work and the supply it produces. And in that sense, not only is it important to know what the how the particular facility functions and how a particular system functions in terms of its network model and prioritization, but also how the repair effort is conducted. And that we model in a construction management sense, using repair crews that have repair resources and can travel along available, so not damaged roads with a certain speed to get to the place where they need to do repair, and there they conduct repair here in this simple model using a constant repair rate. But in more complicated models that we also run, there is a actual construction management process that is very similar to, for example, what John Michael Wong and Kevin Mackey did here in Pier for the recovery simulation of a Caltrans bridge. The simulation of interdependency here was the challenging part, and what we did there is a recursive process where we go in every time step of the recovery simulation through a list of services that are required that are provided by infrastructure systems, and the list of resources that those infrastructure systems demand, and are in this iteration able to capture these loops of dependency that, for example, if there is not enough cooling water for a cellular communication facility, turn that facility off in the next iteration. That facility cannot provide in communication needed for the electric power generator that then is turned off. And finally, because of the lack of power, the water pump is also turned off. And in that sense, we are able to capture the closed loops that drive the interdependency and decrease and substantially affect the resilience of a community. And so here is that community, and this is a nice graphical representation, and this is a little bit more sparse MATLAB representation of the model that's run underneath. And here is a simulation of the recovery process where the red transportation lines and the red color facilities indicate what is damaged, and then the colors change as the recovery process of each individual element of the simulation goes on, until eventually, after some time, the entire recovery process is completed and the community is in some sense back to normal, more or less. Here are then the outcomes of those simulations. This graph is interesting because it shows the effect of interdependencies. The two cases studied are one without any interdependencies, so those internal closed loops are not implemented or not modeled. And the other one is with interdependencies, and this particular one, of course, we chose because there is a large impact of interdependency on the recovery and overall the resilience metrics that we are interested in, this lack of resilience that we are measuring. More can be done. This is just a few examples. Here are basically lack of resilience curves, very similar to loss curves that we usually do for, say, financial losses. And here are mean annual probabilities of a certain lack of resilience that a certain system can develop. And you can see that this particular community is fairly vulnerable to small losses of resilience, small lack of resilience. But as this lack of resilience increases and increases, there is a diminishing probability that it could be so large. And in some sense, this is what we would expect from engineered systems, such as the power system, the water system, the telecommunication system, that have inherent reserves and redundancies. And also we can clearly see the effect of interdependencies that are increasing the exposure of the community. Another thing that this approach affords is a ability to study the sensitivity of the system with respect to the resilience of the community, the sensitivity to particular elements of the system, particular facilities. And here, in this simulation, in this study, we use the Sobol index approach, and based on that, we are able to identify the particular elements of the community, a bridge, a power generator, a water pump, a telecommunications hub, that are causing the most amount of loss of resilience, lack of resilience. And those would then translate into a set of priorities in terms for increasing the robustness of such facilities or for increasing the redundancy of such facilities in the community. Those are the two primary pre-event interventions that we can use to improve resilience, and they have been identified a while ago in this MCR, the Bruno framework. Finally, let me conclude that we have to study resilience, and we have to, as we all saw today, City of San Francisco already does that, realize that increasing resilience, that the community resilience risks are increasing and more resilience is required, even if we do nothing else but encourage population growth, encourage productivity, encourage innovation. All these changes are going to require more and more effort on our side without ever thinking about increasing hazards of climate change to improve the state of our communities. And engineering resilience is a key step to it. We have to be able to adopt rational methods to do so, and to do that we need metrics of resilience, models, and in the end acceptance criteria. And Professor Baker's talk goes a step in that direction, suggesting certain economic acceptance criteria. This is perhaps some element of discussion that we could have here and in the future in our engineering societies about what could be the right ways to encourage measuring resilience, formulating acceptance criteria that would enable design. The framework that we developed at ETH, perhaps the supply and demand framework, perhaps affords a more direct way of doing this design, because we can identify the benefits of individual element improvements on the resilience of the entire community. Before I end, let me thank my students, doctoral students and master students, and of course the postdocs who have been doctoral students with me or here, as for example Marco Brocardo and Panos Galanis, as well as colleagues at the ETH Risk Center and the Singapore Future Resilient Systems Project. So, any questions?